Okay, so our next speaker is Lea Nürnberger, and she's going to speak about optimizations and trade-offs for HElib.
Okay, thank you very much. As it was said, I'm Lea, and I would like to present optimizations and trade-offs for HElib, which is joint work with Amamaria Costache and Rachel Player. And so in a little bit more detail, what would I like to talk about? I would like to talk about one specific scheme, that is BGV, in a specific implementation, namely in HElib, and about a particular problem, that is noise analysis. So we have already heard today that noise may be a problem in FHE, but I would like to get a little bit more in detail. What is noise actually in FHE? How can it be analyzed? And why should we bother? And also, HElib is probably known to most people in the room, but since it's in the title, I thought it deserves its own little slide. So HElib is a homomorphic encryption library that was developed by HElib and Victor Schoep, and offers implementations of BGV and CKKS, including their bootstrapping. And it was first released in 2013, which makes it, I think, the first library that implements homomorphic encryption schemes. And it is implemented in C++. Okay, so to the question, what is noise in FHE? Since I said I'm going to talk about a particular scheme, let's formulate this to what is noise in BGV. And so this is the decryption function in BGV, and there we can see where the noise comes from. So if we've got some ciphertext CT and a secret key ASCII, we decrypt by taking the scalar product between those two. And this leaves us with this term. So we've got the message polynomial, we've got the plaintext modulus t, and we've got some polynomial e prime. And now we can see, okay, if we take this indeed modular t, so the square brackets denote the modular reduction, then this whole term is going to vanish. We are going to be left with the message polynomial modular t, which is exactly what we want. So this is fine. Only one problem. Before we have the joy of taking the whole thing modular t, we are working in a ring modular qi. And so this means if this e prime term is getting too big, we get a wrapper, or we may be getting a wraparound modular qi, but then the dependence of e prime on t may vanish, and we get the message polynomial plus an uncontrollably something, which is not really what we want. So there we got our problem. This is why normally the scalar product between the ciphertext and the secret key is called the critical quantity of the ciphertext. And I hope it became a little bit clear why this quantity is critical. And E prime or T prime are called the noise of the ciphertext. Now, if BGV was a normal scheme in the sense that we encrypt something to a ciphertext, it sits patiently around and waits for it to be decrypted, then this would be no problem, because we could set our parameters at the beginning so that we don't get a wraparound, this modular qi, and everything would be nice. However, BGV is not normal in this sense, and the whole point of FHE schemes is that ciphertexts do not sit around patiently and wait, but that they get modified. And so obviously, if we add or multiply ciphertext, then a critical quantity gets added and multiplied too. So even if everything was way below qi when we started, it is not necessarily so after we evaluated a couple of operations. And so just to give an idea what happens, so for example, if we add two ciphertexts, then the critical quantities get added. If you multiply two ciphertexts, then the critical quantities get multiplied. And there are quite a lot of other operations that also affect the critical quantities and the noise. So to summarize, what is this noise in FHE? We need noise in FHE for the scheme to be secure, but also it will eventually make correct decryption fail. And to know whether the decryption still is correct, to be absolutely certain, we would need to exactly know what the noise is. But if we would exactly know what the noise is, we could just subtract it, and then the scheme would be insecure again. So we need it for security, but then we have a problem with correctness, and if we can guarantee correctness, then we have a problem with security. So the problem with the noise in FHE has been around since the first FHE construction. So one technique to deal with the noise has been mentioned in the talk before, that is bootstrapping. And a second possibility is what is used in so-called level schemes, and that is modular switching. and BGV is such a level scheme. So what does this mean? It means that a chain of ciphertext moduli is chosen instead of only one ciphertext modulus, where we go from lowest ciphertext modulus QO to the biggest top modulus QL. And then to reduce the noise, we can apply something that is called modular switching. And what does modular switching do? So it transforms a ciphertext that encrypts a message with respect to one ciphertext modulus into another ciphertext encrypting the same message, but with respect to a lower ciphertext modulus. And since this is a little bit abstract, I decided to make a very pink animation. Pink seems to be a theme, to illustrate this a little bit more. So at the beginning, we encrypt a ciphertext at the top level. And then we perform a couple of operations, and eventually the noise will grow dangerously big so that decryption may not return a correct result any longer. So then we can switch moduli. That is, we go one lower. We now have a ciphertext that is with respect to one level lower, QL minus 1, and the noise gets reduced by approximately the ratio between QL minus 1 and QL. And so now we have a ciphertext at the next level that has small noise again. So we can perform operations again, and eventually we will have to modular switch again to the next level and so on, until at some point we are at the lowest level. And now here we really do have to stop computing because there is no ciphertext modulus underneath anymore, so we cannot modular switch anymore. So yeah. So now that we had a look at what noise is in FHE, why is noise analysis important? So I already mentioned we need to know what the noise is for correct decryption, but to give a couple of more points. Each modular switching consumes a level until we have no more. So that is, we really want to delay modular switching as long as possible to not waste the levels needlessly. But since if we wait too long with modular switching, we always are in the danger of getting too big noise and not being able to decrypt any longer. For this, we need to have really tight estimates on what the noise looks like so that we can know as precisely as possible whether we still have noise left or not. And also, the ratio between the noise and the ciphertext moduli determines the security level. So if you have a very good idea of how the noise develops, we may be able to set better parameters. Okay, so now that we've established what noise is and why it would be important to analyze it, the obvious question arises, how can we analyze it? And a couple of techniques have been proposed. One is to bound the canonical embedding norm of the critical quantity after each step in a circuit. The canonical embedding norm has very nice mathematical properties which make it nice to calculate and bound, but normally the bounds are not very tight. So then there's the idea of bounding the infinity norm of the critical quantity after each step, which normally is a little bit tighter, but it does not have this nice mathematical properties, so it's harder to calculate. And also we are still getting an approximation error every time that we bound. So if you have a particularly deep circuit, then we get an approximation error at every step, and they cumulate over the evaluation of the circuit, and so the deeper the circuit, the looser the bounds get. Which then gave rise to the idea to say, okay, well, then just bound after the complete circuit, because then you only get the approximation error once. And so this is also what we're trying to do in this work for BGV. So we applied the techniques from the before cited source to BGV, so that was applied to CKKS originally. And also we do this implementation specific for HElib. And I'm going to explain later why we made this choice of actually doing it implementation specific and not for the general theoretical outline of BGV. And so then we compared our results with previous analysis of BGV noise and, as I said, showed the need for an implementation-specific analysis. And we used this then to provide better parameter sets for BGV. Okay, so before I just said, well, we did it as in 5, I now try to explain a little bit more what 5 does. And so the technique is to calculate the variance of the critical quantity after each step in the circuit. And then it is possible to show for at least some operations that their critical quantity actually is normally distributed, which is very good news because we know quite a lot about how to bound the infinity norm of things that are normally distributed. And so in particular, we can say that the infinity norm of the critical quantity with the probability of 2 to the minus 75 is not going to be bigger than 10 times the standard deviation. So then at the end of a complete circuit, we can use like this bound and the standard deviation for the circuit that we calculated to bound the critical quantity. So, and then we calculated the standard deviation of quite a lot of operations, and then ran a couple of experiments where we calculated the point estimator of the experimental data that we obtained to see how closely those match. And very much unsurprisingly, we did this in HElib, and we looked at 8 different parameter sets after 1 to 5 multiplications, and did this for 10,000 trials each. And to give an example of the results that we obtained, so this is after modular switching, and so this is the depth of the circuit that we evaluated. The first columns is the parameter sets, where this is the ring dimension and the maximal depth that these parameter sets allow. And then this first column contains our theoretical results in bits, or the theoretical standard deviation in bits. And then here, this column, sigma s, is the point estimator of the variance that we obtained experimentally. And so the first thing we notice, this is like then the deviation between theory and experiments. And we notice it is always below 1%, but for in this case where it is 1.12% deviation. And so I said we did it over 10,000 trials, which means that the to be expected standard error between experiments and theory is 1 over square root of 10,000, which is exactly 1%. So actually the deviations that we're seeing here is what to be expected when we compare theory to experiments. So we can more or less declare our theoretical results to be experimentally confirmed. And one other interesting thing that we noticed is, so we would have expected to see if you have deeper circuits, that then the standard deviation also grows. But actually this is not the case. So we see here for after for circuits of depth 1 to circuits of depth 5, there's only a very small difference in the standard deviation. So it's actually staying at the same level and the same magnitude, which is very good news because this means that we can use the theoretical bounds that were developed for 1 multiplication also for estimating the noise in deeper circuits, which makes it much easier to estimate the noise in complex circuits. And then, as I said, so we compared with previous results on BGV noise. And so here we have this column that has the infinity norm symbol is the experimental bounds that we obtained in HElib. B infinity is the theoretical bounds that we obtained using our standard deviation. And for example, 27 is the bounds that we extracted from the HElib documentation. And so here we see that we are normally at most 1.5 bits off the infinity norm that we experimentally obtained, and that we're up to 24 bits tighter than the bounds that we extracted from the HElib documentation. And so then we also compared with another work that was done with respect to Palisade. And so here this is why implementation specific actually is important. So here we see again, this is like the bounds that we experimentally obtained. This is our theoretical bounds. So here this is for the noise, not for the critical quantity. This is why the values are slightly different. Here we're about 0.9 bits off the experimental results. And we see that the values that were done with respect to Palisade, they underestimate the noise by about 3 bits. So while these bounds are certainly tight for Palisade, they are no longer tight if you compare them with HElib. And especially, which is quite dangerous, they underestimate the noise in HElib. And if the bounds underestimate, that may suggest to us that we still have noise left and that we can continue to do operations, while in fact this is not the case. So this illustrates, I mean, it makes sense because every library does do their own implementation choices, which are going to affect the noise. But this is just to illustrate that if we want to have an actual good understanding of the noise, We need to look at specific implementations and not only at the theoretical outline of the scheme, or we cannot easily carry over noise estimates that have been done with respect to other libraries. So now, 3/4 into the talk, I finally get to the title of the talk, which is how does this lead to optimizations and why do we need trade-offs? And so we would really like to keep this property that we have observed, that the noise stays constant after modular switching, because then we can use bounds that have been developed for only one multiplication. So how can we then use this to optimize parameter sets? And shuffling quite a lot of things around and doing a lot of arithmetic shows us that we can keep constant noise if we either make the ciphertext moduli ratio smaller, so that is the distance between the ciphertext moduli and the moduli chain, or if we make the special modulus KQI smaller that is being used in key switching. And so we fixed both in turn and saw what this gave us in optimizations for the respectively other one. And so in HElib, the smallest possible ratio between the ciphertext moduli can be 36 bits, but we looked at over 20 parameter sets and never observed in practice a ciphertext moduli ratio that is smaller than 54 bits. And so assuming this, then we can see, okay, for a failure probability of about 1%, and for a ring dimension of 2048, if we compare to the 36 bits that are theoretically the smallest, then we obtain an optimization by about 6 bits. But if you compare to the 54 bits that we practically always observed as the ciphertext moduli ratio, then we actually have an optimization of 25 bits here. And so then we fixed the ciphertext moduli ratio to 36 bits and 54 bits in turn, and looked at this factor by which we multiply the modulus to get the special modulus, k. And so you can see the k that we experimentally observed in this column that has been elegantly glued to the end of the table. And so here we see again for, wrong bottom again. And here we see again for a failure probability of 1% and a ciphertext moduli ratio for 54 bits, we can obtain an optimization of 25 bits for k. So now how does this lead to trade-offs? Well, I already said we can do either or. So in which case do we want to do either or? Well, reducing the ciphertext moduli ratio allows us to squeeze in more levels while keeping the same top bit size. Whereas reducing k leads to smaller evaluation keys, smaller key switching noise, and therefore also faster evaluation key generation. And so obtaining more levels is of interest if we want to make the evaluation of deeper circuits possible. Whereas reducing k can be of interest in client-aided protocols, where the ciphertext is sent to the client for re-encryption, and this is how it's taken care of evaluating deeper circuits, but then we may want to, for example, speed up the generation of evaluation keys. So to summarize, the two things that I wanted to convey is tight noise analysis is really important and worth spending time on, and it's also worth spending time on doing implementation-specific noise analysis. And with 1 minute on the clock to go, that was it. Thank you.
Okay, any questions? We already have one.
Hi, it's really interesting. I haven't looked at HElib since version 0. Because version -1 we wrote for the AS thing. So I found it was really, so they really do have 54 bits as their minimal ciphertext modulus ratio.
Well, as I said, so theoretically 36 bits, but I looked at least 20 parameter sets and just had it print out the ratio between the ciphertext moduli, and there 54 bits was always the smallest that I could observe, even for setting different resolutions for the ciphertext moduli chain.
It's kind of interesting because from memory, I remember 24 was the number we used in the first implementation, which wasn't public. Yeah, so this kind of, so if you really make it smaller, you have more levels, which means you're going to have more computation. You know, you're going to have to. There's going to be more tweaking around. So you've got smaller parameters, but do those parameters actually equate to better efficiency? There's a kind of trade-off, whereas you can, if you keep the ciphertext modulus ratio smaller, you get better noise. But on the other hand, your computational cost may go up because you have to hold more rows of the DCRT matrix and stuff like that. So did you actually look at how your recommendations actually impact performance, is the question?
No, so we mostly only looked at the noise because noise analysis was our focus. So
Okay.
then, yeah.
And then the other question is you said that you looked at that theoretically there's no difference between Palisade and HElib-ish, but then you said that when you looked at an implementation specific thing, you got differences. So obviously there is then a difference between HElib. So what is that difference?
So, for example, one difference would be that in Palisade there's always modular. So, in the end, it depends like where the modular switching is done. For example, going into multiplication, is it done before the multiplication? Is it done after? Because to perform operations between ciphertexts, they need to be at the same level. So, even for addition, so there need to be modular switches at some point. Where are they being done? And that affects the noise.
Hi, thanks for the great talk. Just one question. What you said about Palisade, does that mean there's some sort of security implication or correctness implication since they're underestimating the noise?
No, so the noise bounds are certainly tight if compared to Palisade. So if you're like performing computations in Palisade, then you can use these bounds to estimate the noise in Palisade. The point that I was trying to make is you cannot use the bounds for Palisade and then say, okay, let's estimate the noise in HElib.
Well, if there is a difference between HElib and Palisade regarding the noise because of it, couldn't you say that there's basically a right moment to actually do the scaling? And maybe then is it not more right in a way to do like in Palisade since they can make less noise with their method? Or
Well, you can always get much less noise due modular switching, but then you also lose levels. So then it's a trade-off
so there's
again.
a trade-off actually. Okay, thanks.
Maybe you want to have a little bit more noise at a point, and then you can have more levels, or you can evaluate deeper circuits or so on.
Okay, thanks.
Okay, any more questions? Okay, if not, let's thank Lea again.